Hello everyone and welcome to my channel. Today's topic is multiple linear regression. So without any further ado, let's get right into it. So as you can see here, I've drawn a coordinate system and a set of data points that follow roughly a straight line, but they have a bit of scatter around them. And I've also drawn a function f of x, which is just a line, which of course has equation ax plus b. And as you can probably tell by eye, this function doesn't optimally fit the data. It's not the best we can do. So the goal of this video is essentially to teach you how you find the straight line that best fits these data points. And at the end of the video, I'm going to show you how you can extend this method to higher dimensions. For example, where your function f of x looks like this. ax plus by plus c. So in this case, you have two input variables, x and y, and your model function looks like this. So you essentially have three coefficients. But to get started, we're going to do this in 1D, and as you will see at the very end, this can be extended very easily without a lot of effort. So before we get started, let's do some organization. So essentially we have some data points, xi, yi. So this would be x1, y1, and this would be xn, yn. So what I'm going to do is I'm going to organize our yi's in a vector that's going to contain all of them. So this would be y1, y2, all the way up to yn. And I'm going to organize our coefficients a and b in another vector that looks like this. Then I'm going to write our x values in a matrix, and you're going to see why a matrix soon. But the way this matrix looks is like this. So we have x1 here, x2, x3, all the way up to xn. And here in the second row, we just have ones. And I'm going to show you soon why this is the case. And then we're going to have another vector f. And that vector f is going to contain f of x1, f of x2, all the way up to f of xn. So why is this helpful? The reason this is helpful is because if you write our equations in this way, then we can write our vector f that contains basically the function values for all our points like this, as a matrix vector product between our matrix x and our coefficient vector c. And if you do that matrix vector product, you find that the result is ax1 plus b, ax2 plus b, all the way up to axn plus b. And that's exactly the purpose of that one here. So we can have a value for the intersection of the line with our y-axis. So now we've kind of set the baseline. We've defined our quantities, but we still don't quite know how we find the optimal function. And the key to this problem is to consider these distances. So the distance from a certain point to the function. I'm going to call this dn. So dn in this case would be yn minus f of xn. But as you can probably figure out, if you write your distance dn using just this expression, then it can have positive or negative sign, and we don't want it. So what we're going to consider is actually dn squared. So we can define a function that we're going to call epsilon. That's going to be our so-called error function. And that can be written as the sum from I equals 1 to n of di squared. And theoretically, if we can minimize this function, if we can find a minimum in terms of the coefficients a and b, then we have an optimal solution for our line, and we have found the line that best describes the data points. So to make our life a bit easier, what we have to do is we have to write epsilon also in matrix vector form. And conveniently, this expression for dn and this sum can be written in vector form as y minus f transpose times y minus f. And you can do this as an exercise, see what individual entries or what you would get if you multiply these two quantities out, and in fact you will see that you get exactly this sum here. So before we continue, I'm gonna start a new page and just write this expression for epsilon down again. So epsilon is equal to y minus f transpose times y minus f. And our expression for f that we've shown before is our matrix X times our coefficient vector C. So what we can do is we can plug this expression into our equation for epsilon and end up with an expression like this. Y minus X C transpose times y minus X C. So the next thing we would have to do is multiply these two terms out. But first we have to transpose the first term. And the way we do that is we can just bring the transpose in. So that would be y transpose minus x c transpose times y minus x c. And for those of you who are familiar with linear algebra, you've probably seen a rule for taking the transpose of a matrix or matrix vector product. And that rule is if you have a matrix A multiplied by a matrix B, and you take the transpose of that product, then the result is going to be B transpose A transpose. So you have to switch around the ordering. That's what we're going to do next. And after that is done, then we can just multiply all the terms out individually. So we have y transpose minus c transpose x transpose times y minus x c. So this is our expression for simplified expression for epsilon. And now we can just multiply out all the terms. So if we do that, we end up with the first term, y transpose y, minus y transpose x c minus c transpose x transpose y plus c transpose x transpose x c. And we can further simplify that, and we're going to make use of a very simple rule, and that is that the transpose of a scalar is still the same scalar. So you just take the transpose of a number, and of course it's going to end up the same because it's just a number and not a matrix or a vector. And all of these individual terms have to be numbers because epsilon is going to be a single number. So what we find essentially is that y transpose x c transpose, if you work this out, you can work this out using the same rule as before, is equal to c transpose x y. And because these are both numbers, that means that they're essentially equal. So we can simplify the equation like this and end up with the final form for epsilon. Y transpose y minus 2c transpose x y plus C transpose X transpose X C. So this is our final expression for epsilon. I'm just going to highlight that so you know what we have. But now we've just defined the function in matrix vector form. But what we actually need to do is we need to minimize that function with respect to our coefficient vector. And for those of you who've taken a class in calculus, you probably know that you find a minimum or maximum by taking the derivative of d epsilon by dc and setting it equal to 0. So that's exactly what we're going to do. We're going to calculate d epsilon by dc and set that equal to 0 and try to find a solution for our coefficients. So what you can do is you can just evaluate this derivative with respect to a vector like you would do any other derivative. And I might show in another video why this is the case, but for now just trust me with that. So let's evaluate the derivative. So d epsilon by dc has to be equal to 0. And if we evaluate that, then the first term is just 0 because it doesn't depend on c. In the second term, the c just disappears because there is only one c in there. And we end up with minus 2x y plus, here we have 2c, so we need to get a 2 down, x transpose x c. So what we can do now is we can cancel the 2's and bring that to the other side. And then we end up with an equation x, y is equal to x transpose x, c. So we essentially have exactly what we wanted to have. We have an equation where we have c on one side. And we can solve this equation. But let's start a new page. And I'm going to write this down again. So we have x, y is equal to x transpose x, c. So again, for those of you familiar with linear algebra, there is a thing called the inverse matrix. So the inverse matrix has the following property. If you have a matrix A and you multiply it by its inverse, a to the minus 1, then that's the same as the inverse times the matrix. And that is equal to the identity. So the identity matrix is just a matrix which has 1s on the diagonal and 0 everywhere else. So in 2 dimensions, for a 2 by 2 matrix, this would look like this. So very simple. So what we have to do in order to solve this equation is we have to multiply both sides by x transpose x to the minus 1. So the inverse of x transpose x. That's going to be a 2 by 2 matrix. So if we do that, we end up with x transpose x to the minus 1 times x. I think there's a transpose here. Times y is equal to x transpose x to the minus 1 times x transpose x. So there is a lot of transposers in there, times c. And this product here is just the identity. And if you multiply the identity by c, then that's just going to be c. So essentially we have found that our coefficient vector c is equal to x transpose x to the minus 1 times x transpose y. And this is our final solution. If you calculate this in NumPy, for example, then you will find that you set up your matrices like we've shown before, and you calculate this in NumPy, you find exactly the line of best fit. And now if you want to predict another point, so let's draw our coordinate system again. So that is xy. We've found our line. These are our previous data points. This is x. This is f of x. Now say we want to predict a new point. We want to predict what our function would be at that point. Say this is the true value, so this is a test set. Our function would predict that value, which is reasonably close. And we've achieved our goal. We have found the line of best fit. So while this is fairly useful, you might wonder how you can do this in higher dimensions. In machine learning, a lot of the time, you're interested in very high dimensional problems where you have a lot of input variables, and not just one input variable, like in this example. So the way you do that is you just extend your coefficient vector. So your coefficient vector is going to contain coefficient C1, C2, all the way up to Cn. And Cn is kind of n is the number of coefficients that you want to have. So the number of your input variables. And the other thing that you have to do is you have to change your matrix X. So now your matrix X is going to contain x11, x12, all the way up to x1n. And then you have x21, x22, x2n, and that goes down to x lowercase n 1, and here it goes up to x lowercase n capital N. So here capital N is the number of coefficients, and lowercase n is the number of data points in your training set. And if you can use the exact same equations if you set up your matrix like this and your coefficient vector like this, you have to solve the exact same equation, and that's how you end up with a solution for your multiple linear regression problem. So I hope you enjoyed this video, and if you did, hit the like button and the subscribe button and drop a comment below. If there is anything else you want to hear about multiple linear regression, or if there is any other topic that you want me to discuss. Thanks for listening and see you next time.